Hi everyone. Thank you for joining me today. So, open source software in automotive system is well known for accelerating the development, enhancing performance, and fostering a vibrant ecosystem, and offering clear advantage over proprietary solutions. However, achieving the safety and security requirements with open source remains a significant challenge. So with a few real-world case studies to guide us, today you are going to hear several compelling real-world stories from our experience. So here's the agenda to help you follow along. So to set the stage, I will spend a few minutes to introducing our open source history and our work in automotive, especially for those who are not deeply familiar with automotive. Next, I will share an open source safety and security consolidation approach that we have refined through the proven production experience. Then we will dive into how we see the opportunity to validate the open source software in automotive. It was quite an adventure with ups and downs. So by sharing experience from our production case, I hope to inspire the newcomers, learn from our mistake, and avoid to make it again. So, a slightly introduction. So I'm from EMQ, I'm Jaylin. So we are a global open source software company. We take safety and security very seriously. We believe the trust is non-negotiable in mission-critical scenarios. So here are some of the highest security standards we have achieved. So these certifications just underscore our dedication to delivering the reliable open source solution. Okay. We have consistently contributed safe and secure software for the Internet of Vehicles and software-defined vehicles. And to deepen our commitment, we joined the ELISA a year ago, and we donate our two major components in our solution here, so which is LVH, NanoQ, and eKyper. The NanoQ plays a crucial role in soft SD-WAN here. It acts as a multi-protocol proxy and in-vehicle broker and the messaging queue. And the eKyper, which is a universal stream engine in vehicle. So as shown in architecture diagram here, so basically the NanoQ aggregates the data from CAN, SUM-IP, MQTT, and other data sources, ensuring the low latency and high throughput interoperability. It also acts as a persistent messaging queue here for historical data queries. And eKyper subscribe to upper part is Kyper. Subscribe to the top nano MQ topics, which fuses data from the various sources using string computing with hundreds of rules and operators. So this contextualizes the data, refines the raw data into actionable information, and which identifies the patterns from the data. So ultimately, those insights are reported back to the cloud to drive the business forward. Okay, so what you have heard is the essence of the data closed loop, so which is a widely adopted methodology in software-defined vehicle for enabling remote diagnostic and speeding up the time to market. So it delivers the flexibility, interoperability, and real-time data processing. So transforming the static vehicle into dynamic one, also an intelligent extension of customers' daily life. So for automotive OEMs, so this also represents a paradigm shift from the case-driven to the data-driven operations. So in essence, the data is the new lifeblood of the industry, and the data closed loop serves as the vessels and the pumps for the data. So we are really productizing and forging open source software into an automotive-grade data closed-loop solution here. Just a quick look at our customer logo wall. So we have served more than 1,000 customers. Just to prove, I'm not joking. We are not newcomers to this industry. So we're gonna focusing on the IOV and SD-WAN part today. Okay, enough of the background knowledge here. So we all know there is a gap between the open source and project and automotive safety. Fortunately, the community have accelerated our security consolidation, especially at the early stage of project. First, we don't think open source is just the code dump on the GitHub. We believe it's a vital communication channel between the maintainer and the users, a knowledge sharing space that extends beyond the project itself. So yeah, it's like a thriving forest here. So the trees represent the automotive, represent the open source project, which provides the shade for the surrounding plants. The plants represent the free users, while the plants enrich the soil represents the maintainers. The soil nurturing grows in return to the trees through the fix and the feedback from the free users. So as an ecosystem, we all thrive together. However, a forest needs inhabitants to flourish. We started as an IoT project, but evolved to serve both industrial IoT, SDV, IoV, and robotics, and so on. So, which broadening our user space to capture diverse voices from the community. And open source is also like your promise to the world. So like we all see some other open source project being abandoned after months or years, usually because the maintainers cannot afford the time or money to keep it going. Also, our 3 core ones all have endured over 5 years. Yeah, so this is start history of our project, so which reflecting our unwavering commitment to open source. And we also follow an open core philosophy here. So open core means keeping your core part open while building a specialized part like SDV or industrial IoT part extension on the top of your cores, which fosters collaborations. For example, there's a smart home users found out a concurrency bug in your project in their home from their home deployments, which leading to a fix within a day by us. So which prevents impacts on the production vehicles because the core part is reusable at other place. So it's mutual. So imagine you can spotting a bug that in your home that averts an automotive recall. So that's the power of community. And we also collaborate with other open source projects to build an ecosystem, like the Nano Message and NNG. So here is a picture showing the historical bonding between NanoMQ, NNG, and ZeroMQ. I'm not gonna go into deep, but so we inherited the history legacy from the ZeroMQ. And also, EdgeX Foundry is a well-known industrial framework for IoT 4.0. The eKyper is already the standard streaming engine of EdgeX Foundry. Okay. Last but not least, the humility and the honesty are the keys. So here I'm going to give a story about how academic work help us. So as a open source maintainer myself, I admit that we lack the testing resources like those proprietary softwares, and we made mistakes, a lot of bugs, and we have built a transparent community here, welcoming the security experts and openly discussing CVEs. So to attract experts, we tackle the tough problems. We make our topics more interesting for them. So NanoMQ is an ideal example for this. So which is ideal for next generation fuzzing tools. So the story is like this way. Cycles repeats again. So the researchers from the institution or university engage us for the vulnerability hunting. So they usually they give their assumptions or suspicious point, and we refine their production methods, which helps them yielding a better data samples for POC, so that we can provide the quick fixes. So here are 2 examples here. Both of them are published papers. So in case you don't know, the fuzzing is a stress testing technique, which is testing your code with random inputs to uncover the crashes or flaws. So for But for stateful protocols like MQTT and some IP, and parallelism broker messaging bus like NanoMQ, the traditional fuzzers is not so effective on spotting bugs. So basically, the data coverage is not high enough because it is only simulate one client or missing the multi-party dynamics. So basically, it can hit every logic branch in your code. But innovations like MB fuzzers and SP fuzzer here, they address this problem. So the MB fuzzer is which is a fuzzer that uses a Q-learning scheduler to select the messaging type intelligently and mitigate and mutate them, which can exposing those hidden state errors in your software. Yeah, and SP fuzzer is another stateful fuzzer that can fuzzing your broker and the messaging bus parallelly, which is enabling a high-performance fuzzer. So it helps us address the parallelism, concurrency, disordered execution, data racing, those pitfalls of commonly seen bugs in high-performance systems. And regarding automotive, then where our part is managing the high-throughput SDP data, this could delay the signals or cause crashes, so which eventually going to result in the safety issues. By collaborating with the academic world in SDV, the community eyes help us to speed up development while also preserving security. So without community-driven research, and we believe we wouldn't be vehicle production ready so soon. Okay, but community and academic researchers, they can only help you to find the bug and identify the bugs. So now the burden shifts on you. So how do we fix them and meet the users' expectations? So first of all, to debugging a bug in automotive is not a pleasant experience like you're debugging a bug in kernel. So basically, the vehicle is in your customer's hands, and you cannot not just remotely log into their vehicles and applying GDB or address sanitizer to identify which part it goes wrong. Yeah, so we need another approach. And I would like to first clarify that there is also a misalignment between the standards like ISO 26262 and IC 61508, which they are designed for single-threaded deterministic systems. However, the modern operating system and the middlewares all utilize the CPU features like out-of-order execution and multi-core parallelism for better performance and low latency. So it introduced a new probabilistic issues like data racing and data lock contentions, which is not well handled in the old safety hardening approach. So I was pretty disappointed when I discovered that, and we found another way out. So inspired by the Erlang's actor model. Erlang is another programming language developed by Ericsson. Okay, so the actor model means everyone is actor. So the actor model actually isolates the process, communicating via messages to avoid the shared state and the serialization bottlenecks. So usually when you need to reuse a block of memory, you in two threads, we don't only copy them, but we pass the memory or pass the workload via a message. So every processor has a mailbox. It did something specific when it received the message. Okay, so here is a memo shows help you understand what is actor. So for a single-threaded program, the one strong dark here shares the free lunch of performance from the advancement in the semiconductor industries. So the CPU frequencies keep going high in the past decades. Yeah, but however, nowadays we shift to the multi-core approach. Then the single-threaded will waste other cores. Let the other ducks just sit and watch. Only one duck is doing all the job. Therefore, the actor model is here to slice the workload into pieces, then distributing them equally to the old ducks here, and aka Yeah, cores. Every DAC is a core, a computing core in your system. So which benefits the overall system performance. Okay, but now maybe does this paradigm gonna solve all problems? Not, because basically we cannot eliminate all the shared object because we need to minimize the memory usage. So we learned another lessons. So we still got a shared object. So that's why we add an actor replay features to reduce the testing works. So on the right is an example here. Let's take NanoMQ as an example. So basically, every rectangle here represents an actor. Each actor runs through underlying actor thread, and each actor interacts with those other actors sits beside them. Yeah. Okay. So taking the bridging actor here as an example. So for the bridging actor, we record the message flows and replay the buggy scenarios to pinpoint the data races. So here, each message flows from another actor triggers a logic branch. So there are two messages gonna reuse one shared object, which we call the data racing bug. Then we can replay the message to discover what went wrong. Yeah. So, and I know it's like a aftermath rescue. It's not a silver bullet for all open source safety issues, but it let us locate the problems and fix them in one day in most cases, and even in the customer's hands, from customer's hands. Yeah. So since we don't have the luxury to put heavy load testing on one of our open source project, so and the debugging automotive software is always struggling. Yeah. So that's why I'm emphasizing the importance to pinpoint the problems from the project itself. Okay. The toughest challenge often surfaces post-development after going to the market. So now our real-world adventure begins. Okay, so in our largest project yet, we were selected by one of the top-tier global OEMs to resolve the chaos left by our predecessors. They hit by a common open-source liability trap. So they built a similar product like us. So it's a data closed loop solution. But they treated it a transactionally way. So they relying on the Spark and the Paho, Eclipse Paho. Those open source projects are Paho is Eclipse SDK. Spark is a streaming engine which is built for decades ago. So the Paho as a vehicle to cloud data backbone here. So although the Paho was a small piece, but it becomes the system's cornerstone because all the data relies on it. So to the cloud. So all seems stable until they launched the product to the market. The connectivity issues emerged. The packet drops, delays, and floods, even causing the self-DDoS attack. So, and they dismiss them all as network problems, and we later prove they are not. Otherwise, yeah. So this highlights a software supply chain risk. Yeah, a simple open source component in your solution can be pivotal in safety critical scenarios. But don't get me wrong. Paho is a solid, widely used MQTT SDK with multi-language support, and we have benefited from it too. However, you must deeply understand what it is made for before using it. In this case, the Paho is not built for automotive scenarios. They are trying to force it into a role which it wasn't designed for, which led to their ultimately downfall. So it can be also concluded as a know-how mentality, which is a commonly used word in automotive. So beyond connectivity here, the traceability and observability also falters. The clouds sometimes receive the non-essential sensor data from vehicles, like the battery currents jumped over 1,000, and the speed oscillating between the 0 to 258. So basically it's kind of like the driver is doing is traveling through the black hole. So all these non-essential data so breaks all the data closed loop, makes the cloud analyze basically not workable, and even worse. Their lack of performance monitoring and resource limits turned controllable issues into a totally disasters. So they found memory leaks in the program, and the CPU spikes eventually freeze the IVI system, affecting the other surface in the IVI system. Even worse, they would like to solve the bug by retrieving the logs, and the excessive logging eventually overwhelmed the cloud, which blocks all other vehicle-to-cloud services. So they have to go on site and collect their log or initiate the recall. Okay, after we step in, so we took different tactics. So we're building an end-to-end open source stack from the scratch for full visibility, and from the AutoSAR AP layer to V2X channels to the cloud, yeah, and even the factory, yeah. So from vehicle to the cloud to the factory, we can cover all the data links and the protocols of the source project here. And so we forge a trustworthy open source with automotive know-how mentality, which may sound dumb because basically you did all the work, but really effective here. So, and we also assess the third-party dependencies for safeties carefully, because when the integrating only those we know well, those libraries, those open source libraries, the liabilities falls on our shoulders when we using them in our project. As for the connectivity part, so we enhance the bridging with the QoS prioritization, auto buffering, adding canceling timeout to mitigate the issues. So we don't have time to go into details here. So just give a story explanation. So above all, the traceability and observability and tunability are the safety's cornerstone here to us. So our end-to-end infrastructure traces the data across the complex topology in the vehicle and beyond the vehicle to the cloud. Yeah. So which help us to pinpoint the anomalies like malformed ECO data, which gonna cause the misbehavior of other domain systems. So now we understand those non-essential data, where those nonsense sensor data come from. Because the ECO sends out malformed data, which is just like a fuzzing packet, which causes like bytes overflows in the other domains, which basically then produce a false result to the cloud. So now you know how the traceability matters in the vehicle. And this methodology also helps us to discover several other issues like a low MTU setting in the kernel, in the T-box part, which cause the TLS handshake failures. Those problems could linger for months if without such a clear evidence from our tracing. Yeah, but we made mistakes too. So take STR as an example. The story gonna be long here. The STR stands for the suspended to RAM. So a little bit spoiler ahead. So it was our core part to be blamed. So architecture looks like this way for your easy to understand. So the story starts like this. So one morning, a customer call woke me up. A severe issue found in a new high-end car series. The data links broke. Our process went into abnormal state after the STR triggered. And the process went into zombified after exiting STR mode. So background knowledge is STR is a feature to enable faster startups, to boosting systems speed, allowing the vehicle system to go into sleep mode and wake up quickly just like your laptop. So when you're developing the STR feature, you need to carefully aligning your the time frame between the kernel and your software and from the user space. Yeah. By hearing STR, so I know we were really in trouble, because this feature it haunted us during the development and the delivery days. We really rely on sending a signal termination to our sub process here, and adding a new STR proxy to act as a STR manager. So, and we convinced ourselves that when you rely on a kernel, it means lowest risk. And after testing, despite the lack of confidence, we release the feature to the market. After all, the customer is pushing. So it was a classic case of wishful thinking, setting a trap for us later. Then the Murphy's Law is proved. We have to pay. So the problem is pretty hard to reproduce in a testing vehicle, with a low probability made debugging tougher. So we need more clues. Okay, now the debugging began. And then after retrieving some system logs from the vehicle, sorry, it's not it's not big enough. Okay. So the system log is like the top log, process states, and Android log catalog. They showed the process went into abnormal states after a frequent STR entrance and exits, hundreds of times per minute. This is not as we were being told when we received the requirements, and also not quite normal in your vehicle. So unlike, okay, so, and the process that should die also lingered randomly. Okay, so then we guess perhaps that's the reason. But we cannot reproduce only by simulating the entering and exiting STR locally. So and additionally, some accident. Okay, some report also says that there is subsequent issues. Some of the battery in cars gonna drain out after the problem happens. So apparently, yeah, there were missing pieces. So we keep digging. So after retrieving some, we just expand the actor replay the message to replay what happened before the process went into zombie mode. And we found out that there is a crazy reconnections of the diagnostic client, which finally exhausted the Linux socket file descriptors. So it's a FD exhaustion. The client is the diagnostic client here, which is an Android application, which is responsible for flexible remote diagnostic. It reads data and from our bus and push the raw computing methodology to the eCapper here. So basically, this when the FD is exhausted, it blocks the signal from the reclaiming FDs, failing the STR process graceful shutdowns, because the STR manager have to wait PID, then wait until the process exists. So also this case also will cause the battery drains, because each time the diagnostic client reconnects, it pulls the diagnostic return message from our messaging bus, so it triggers the diagnostic process again. So it will fire a request to change the battery mode of the vehicle. So yeah, so the vehicle keep entering and exiting the STR mode. So you can see that actually no one is going to be blamed here. This is except the diagnostic clients, because they misuse the PAHO client SDK. Yeah, Eclipse PAHO again. So in MQTT protocol, there is a rule that the same client ID only can preserve one alive connection. So basically, they reconnect it themselves and kick themselves again and again. So which result in an infinite reconnection. Okay, so therefore this is an issue that can only happen with complex prerequisites, and it still happens with no one to blame. Okay, I guess we have running out of time. So just a shout out to the community. So there are some side stories. I'm not gonna to go through of them. So in a connected vehicle, demands a connected safety approach. So we need to, I believe, tackling challenges from an architecture perspective and forcing robust ecosystem, especially from open source perspective, is the way out for us to deploying open source software in the automotive. Okay. Do we have time for question?
What kind of activity did you do for ISO 26262 and cybersecurity certification?
You mean at our company, or you mean at the case I shared today?
For your solution.
For my solution.
You mentioned it's for the automotive. You made some kind of communication box. So what kind of activity did you do for the
To meet ISO 26262.
Safety certification.
I know. Yeah. So I talked about this before. So I believe ISO 26262 is not well designed for the open source part, especially for those multi-threading middlewares, and we pay the money to go through the certificate. However, we found that their approach is not quite useful for us. So in the end, so as you know, in China, or recently we didn't apply the ISO 26262 in all the vehicles. So we have our own way to save for safety. Yeah. Another?
So were there any barriers to get certification for the automotive industry with that solution? Any barriers to get certification with that your architecture?
Well, money? Yeah, I don't think there's a barrier to get certified, as long as you know your software and you can.
We didn't use any open source project. I guess there are any barriers with that certification.
Okay, here's the case. If the open source project is not written by you, then basically it's going to be a tough experience for you to rewrite part of them to meet the standards. And in our case, the open source project is maintained by ourselves, so it's not hard for us to meet the standards. Yeah. Any more? From the guy first.
Can I ask a question? So there are many problems during the suspect phase. So were they are solved or not?
Of course, they are solved, because the problem is caused by a crazy reconnection from the diagnostic client here. If we resolve the crazy reconnection from that Android application, everything works normal. Yeah, and also there's another shout out to the ELISA. So the FD exhaustion case is not being introduced into a standard. There's no standard way to deal with it. I believe the kernel shall be like firing a warning or even kill the process when it exceeds the FD numbers. Yeah.